Welcome back to the session. So in previous sessions we've been talking about one sample t-tests and concepts like accuracy of a test, what does sensitivity, specificity, type 1 and type 2 errors mean. So now that we've covered the basics of hypothesis testing, what does p-value interpretation mean, we're going to move on to a few more tests. Primarily, how do we handle multiple samples when we are comparing them against each other? The first test that I'm going to take is a two sample t-test. Uh, what the two sample t-test essentially is going to check is whether these two samples that we are testing, are they coming from the same population or not? And uh, why would we want to do this test? I will cover this in the second part of the video. Now, assuming that you have two samples, let's say sample A and sample B. Sample A could have a mean, let's say, so let me just draw it out. So we've got, let's say, sample A, which has got a mean of, let's say, mu1, or rather, let's keep it in our definition. So let's say x bar 1. And I've got sample B, which has got a mean x bar 2. And let's assume for a fact that x bar 1 is not equal to x bar 2, right? And x bar 1 or the sample A comes from a population which has got mean mu1, and sample B, which has got a mean of x bar 2, comes from a population which has got a mean of let's say mu2. Now just because x1 is not equal to x2, can we say that mu1 is also not equal to mu2, right? Or that population of A is different from population of B? Are we sure, or are we 95% sure? Now bear in mind that whenever we extract samples, it's quite unlikely that two samples will ever be equal to each other. So x bar 1 might be, let's say, 9.99999, and x bar 2 might be equal to 10.00001. Now just because 9.99999 is not equal to 10.001 does not mean that the population mean of these two samples, or these two samples may actually be coming in from the same population. It could be that population A and population B are the same population, and sample A and sample B are simply two different samples extracted from the same population, right? Now if we have two different samples extracted from the same population, it is overwhelmingly likely that those two samples will not be equal to each other. But if they are coming from the same population, those values are likely to be very close to each other. So how do we test if two samples that we've got, are they coming from the same population or are they coming from two different populations? So here we apply a two sample t-test. The null hypothesis being that both samples are from the same underlying population. An alternative is always the opposite of the null, which says that both samples are not from the same underlying population. Now before I move on to how to conduct this test, we're going to cover a little bit of theory and how does a t-test actually solve this problem. And as I mentioned earlier, every hypothesis test is going to use the central limit theorem over here. So I want you to think about how do we going to apply the central limit theorem to solve this problem. Let's start with the assumption that I have a population with mean mu1, or let's say just mean mu over here. And let's assume that this is the population, or this is the sampling distribution. So if I start extracting samples from this population with mean mu, my samples are going to follow or the sample means are likely to fall on a normal distribution around the mean, right? Now this is what the central limit theorem, or the CLT, tells us, that the sample means are going to follow a normal distribution around the actual population mean. So I'm quite likely to extract samples, let's say, within this area, or a specific confidence interval. We can call it, let's say, the 95% confidence interval. So 95% of my samples are going to lie in this population, this shaded region which I am coloring over here. but there's also likelihood that my samples could lie over here and over here. Let's assume that I extract two samples. One sample, sample A, lies over here. So this is sample A, and I extract another sample which is say over here, sample B. Right now, the sample A and sample B. Now, the mean of sample A, I'm just going to call it A, is definitely not equal to B. But as we can see, these two samples are coming in from the same underlying population which has got mean mu. So how do we test whether these samples are coming from the same population? Right? So there's one roundabout way of we can actually go ahead and do the test. I can take sample A, do a one sample test, and test whether sample A is coming from mean mu or not at, let's say, 95% interval. I take the sample B, again do a one sample test, and test at 95% whether it's coming from population of mean mu or not. If in both the cases the null is retained, that means we're essentially saying that A is coming from population mu, B is also coming from population mu. Hence A and B, they don't have any significant difference from each other because they are coming from the same population. That's one way of looking at it. The other way of looking at it is, let's draw out the sampling distribution around A and B itself. So I'm going to take another diagram over here. So what do we have? We don't know, when we have extracted sample A and sample B, we don't actually know what is the population mean they're coming from. I have two samples A and B. In the previous example, we were testing it against a population mean. But in real life, there is no population mean. We don't know. We are only working with sample means. So let's say this is the mean of sample A. And let's draw out the distribution for this. Let's assume that the mean of sample A follows this distribution. And I've got sample B as well. So assuming sample B as the center, I'm going to draw out the sampling distribution likely to come from B over here. So as we can see, there is an overlap between the two hypothesized distributions of sample A and sample B. Now, if this shaded region is large, what does it imply? If this shaded region is small, what does this imply? Right? So if this shaded region is large, right, it would imply that the probability of the population mean lying over here for both of these two samples is very high. In that case, it's quite likely that A and B are coming from the same population. But in case this shaded region is very small, for example, let's take an example where the shaded region is very small. If A and B are very far from each other, let's say A and B are very far from each other. Instead of being very close, I'm going to draw it as very far from each other. And here we have the normal distribution for around sample A. Then I have the normal distribution around sample B. And as we know, a normal distribution effectively never touches zero. So the shaded region lies somewhere over here. It's very, very small. It's actually going to be the p-value or the region is going to be actually less than 0.0001 in this case. In this case, the p-value could be very large. Let's say p-value is definitely greater than 0.05 over here. So in case A and B are very far away from each other, then their distributions are unlikely to have a large overlap. In this case, A and B are more likely to come from two different populations. But let's say A and B are very close to each other. In that case, the sampling distribution is likely to have a large overlap with each other, and they are more likely to come from the same underlying population. And this is what the hypothesis test is going to check. And the p-value that we generate in a two sample test is simply the area of the region in which both the distributions are overlapping. And if this area is large enough, then we're going to go with the null hypothesis. If this area is very small, as in this example over here, we're going to reject the null and go with the alternative hypothesis. That being said, right, how do we determine whether A and B are close to each other or A and B are very far from each other? And just like in hypothesis testing, you cannot look at the mean and make any decision. You need to look at the standard errors around the means that we have generated for the sample. And looking at the standard errors and then the difference between the two, we figure out whether the two differences are significant or not at the level of alpha that we are setting. So mostly the alpha is set at, let's say, 0.05 level, or we're testing it at 95% level, but there's no rule around alpha. And as I've mentioned it in the previous lectures, depending on the cost of doing a type 1 and a type 2 error, we're going to set the alpha at whatever value that we want to. For example, over here, where we know nothing, we might go with an alpha 0.05, and if the p-value is greater than alpha, we go with the null. If p-value is less than alpha, we obviously reject the null and go with the alternative. Therefore, alpha is the probability of us committing an error, and we are okay to commit an error 5% of the time. But that doesn't mean the same thing when we are doing disease testing or pregnancy testing. One kind of error is always more harmful than the other kind of error. Now, looking at this two sample test that we've checked, can somebody tell me, or sorry, can you figure out what would be a type 1 error and what would be a type 2 error? So which kind of an error is a type 1 and which kind of error is type 2? The two kinds of errors that we can make over here is that A and B are from the same population, right? But we end up rejecting the hypothesis and we say that A is not equal to B, or the population of A, in fact, is not equal to the population of B. That's one kind of error. The other error is that A and B are in fact from the same population, are from different populations, and we end up saying that population of A is the same as population of B when it actually isn't. So these are the two kinds of errors, and if we want to fit it in as type 1 and type 2 errors, let's go back to the definition on the slide. So type 1 error is rejecting the null when the null is true. So what is the null in a two sample test? In a two sample test, the null is always that the mean or the population of A is the same as population of B. They are the same. Or I can say that population of A is the same as population of B. So when I commit a type 1 error, I reject the null when the null is true. So I end up saying that population of A is different from population B when in fact they are the same. That's a type 1 error. A type 2 error is accepting the null when the null is false. I end up saying that population of A and population of B are same, or I say that A and B are not significantly different from each other when they are in fact different from each other. That would be a type 2 error. So now that we've established the basic application, or the basic background of what a two sample t-test is doing and how it actually works when we are looking at the sampling distribution, I'm now going to talk about the business application by taking up a few examples. So moving on to a few examples of two sample t-tests. So I'm going to open the HSB data over here, and we've already worked a lot on this data. So we've got the scores of the students for different subjects over here, and we've got a few information regarding the profile of the students. The one which I'm going to use is this gender variable, or the female variable, which is a binary variable 0 or 1. What this variable essentially does is it divides the data into two samples, males and females, and we've got the mean scores for these two genders which we can compute. So let me draw it in Excel over here. So I want to compute the mean score for, let's say, math. Okay, some problem in my pivot table. Let me just do it again. So pivot table, yeah, it worked. So this is the mean score for math for the full sample, but assuming that I've got two samples, one for male and one for females. So let me remove the blank, and there we have it. So for the two samples that we've got, the mean is different, and as I explained, it's very unlikely that two samples will have the exact same mean. And the reason why it can go into multiple decimal digits, and always be different for each other. So we've got approximately 52.9 for gender equal to 0, and we've got 52.4 for gender equal to 1. We want to test whether gender has any impact on math score or not. right? So a two sample t-test is essentially going to test the impact of gender on gender of the child on the scores of the child. And we've got a sample of about 200 students. Roughly half of them are males, half of them are females. We've got the mean score for males, and we've got the female mean score for females, which is 52.9 and 52.4. So prima facie, it does appear that the two genders have the almost exactly the same score. But what we are assuming is that this difference is not significant, right? And it always pays to test the significance of any particular statement that we are making. While this difference may look very small, but if our sample is large enough, this difference could actually be highly significant, and we could say that 52.9 is actually significantly higher than 52.4. So we can't make a blanket statement just by looking at the means of two samples. We have to test the difference between the two samples. So in this case, when I am testing the impact of gender on the performance on math scores, so my H naught, or the null hypothesis in this case, is going to be that gender does not impact math score. Why do I say that? Because the H naught in a two sample t-test is always that these two samples are coming from the same population, or we saying that male mean score is exactly the same as female mean score. So this is my null hypothesis. The alternative hypothesis is that yes, gender does impact math score, or male scores are significantly different from female scores. So please remember that in two sample t-tests, we are only testing the equality or not of two samples. We are not testing as of now whether sample A is greater than sample B. We are not doing a tailed test of the tail in either way. We are not assuming that either sample A is greater than B or B is greater than A. We are simply testing whether A is the same as B or not, or whether A and B are coming from the same population. If in fact gender does not impact, that means these two samples are coming from the same underlying population. There is no difference. But if gender does impact, that means the male scores are coming from a different sample as compared to female scores, i.e. they are performing differently on the underlying score, on the underlying uh, performance of the subject. So given a context over here, now I'm going to talk about how do we actually go about doing a two sample t-test. Now the procedure to do it across all different tools is almost the same, except in SAS obviously we have to write some code. So I've got the example SAS code for doing a two sample t-test, and we're going to look at the independent samples test first. I will cover paid samples later. So the independent samples test syntax lies something like this. So proc t-test data equal to data set name, class category var test var. So class category, so class is the variable in which we have to specify the factor which controls the two samples. So over here we've got proc t-test data equal to, so I've got the library name which is data itself, and the data name is hsb2. So I put in hsb2 over here. Class, so class is the variable which creates the two samples. So in this case that variable is female. So female is a binary variable. It's got two different values. So it will assume a sample is based on these two values itself. So class female. So every different level in the female variable, it will test it out. The variable that we want to test out is math. So I'll copy math over here, and we get var math over here. And I'm just going to put in ODS HTML to get an HTML output, and that's it. So proc t-test data equal to data set name, class, the sample variable var variable, the variable that we want to test it out. I select this, I press F3, and I get my result. Or why did I get my result? Okay, I've opened the dataset is already open, so my bad. Let me close this dataset and run it again. And there we get the result. So this is the text result, and this is the result for the t-test on the HTML method. So if I look at the p-value over here, so this gives us the p-value of the two tests. So two different ways of conducting the t-test, equal and unequal variances. I'll come to that later. So let's have a look at this particular table that we've got. So we've got two different levels for female, 0 and 1. So they are assumed to be the two samples that we've got. So gender equal to 0 has got 91 observations, gender equal to 1 has got 109 observations. So please remember, in this kind of t-test, it does not matter, or it does not require sample A to have the same number of observations as sample B. So sample A has got a mean of 52.9 that we saw in Excel as well, and sample B has got 52.39 or 52.4 that also we saw in Excel. We've got the standard deviation of the sample. Looking at the standard deviation, we can calculate the standard error. Once we have the standard error, we can generate the distributions around male and female for the math score and figure out what percentage of the area is overlapping. And we've got the minimum and maximum for each of these two values. So over here we test the difference between the two samples, and this is the pooled standard error and the pooled standard deviation for these two samples. So we don't need to go into the exact formulas over here, and we can test the means for both of them over here. So we've got the mean over here. We've got the 95% confidence interval for the mean. Now please note that the 95% confidence interval around the mean is simply mean plus minus 1.96 times the standard error, or about 2 times the standard error around the mean. So that gives us the confidence interval of the actual population mean. And as you can see, the 95% confidence interval for both sample A and sample B appear to overlap to a large extent. And the degree of that overlap is given by the p-value over here, which is 0.68. Now 0.68 is much higher than the value of alpha, which is 0.05. So as we mentioned earlier, if p-value is high, we actually go ahead and accept the null hypothesis. If the p-value is low, null has to go. So in this case, the p-value in both the interpretations is high. It's 0.68. So our null stays. So what was our null? Our null was gender does not impact the math score, i.e. math scores for both males and females are essentially the same. There's no difference between them. Gender has no impact on math scores, and our significance test is also telling us that. Now there's one difference that we need to look at when we're doing two sample t-tests, which is that whether should we look at the equal variances formula or unequal variances formula. The reason behind this is that when we extract two samples, the two samples may be of very different sizes. And if the two samples are of different sizes, they are likely to have different standard deviations, because standard deviation is dependent on the number of observations also that we pull to a certain extent. To make sure that standard deviation or differences standard error don't bias our results, we have two different t-tests running. One which assumes equal variances in the sample, the other which assumes unequal variances. Both of them can give us very different results as well. Right? So how do we test, or how do we know which one of these to take? An easy method of looking at it is we look at the equality of variances test over here. It's given in SAS. And the null hypothesis for this test is that the two samples have the same variance. Alternative two samples have different variances. We can see the p-value for this is actually higher than alpha. That means these two samples have equal variances. Therefore, we can look at the pooled variances result over here. But I would recommend that you actually ignore the equality of variances table. As a rule of hand, whenever these variances are equal, and please make a very important note of this, if the two variances are equal, both equal and unequal variances test will give the same result. If the two variances are unequal, we as it is have to look at the unequal variances column. So as a rule, I suggest, and you can either choose to use the same technique or you can ignore it and look at the equality of variances test as well. I suggest that we always look at the unequal variances formula or the unequal variances result. Reason being, this unequal variances t-test formula can handle both equal as well as unequal variances. To be on the safer side, I always prefer to look at or assume that the two samples may not have may not have equal variances, and always look at the unequal variances t-test. So this was an example of two sample t-test using independent samples. Now, there's a great confusion what constitutes an independent sample and what constitutes a paired sample. So we have two types of two sample tests, independent samples and paired samples. So independent samples typically are, so we've got independent samples and we've got paired samples. So independent samples are two samples which do not overlap between each other. So there will be no overlap between them. So if you're testing the impact of gender, every observation is either a male or a female. You can't have an observation which lies in both the samples together. So there is a strict differentiation between the two samples. The two samples may be of equal or unequal sizes. Paired sample, on the other hand, is more to do with repeated measurements, repeated measures on the same sample. So what that essentially means is I'll give you an example. Let's say that we take a sample of 10 people and we measure their weights. We take their weights before a diet. So we measure weight before diet, and then we subject them to a diet. It could be an Atkins diet, it could be a vegan diet, a vegetarian diet, a low calorie diet, a high calorie diet, or whichever diet that we want to do. And for these same 10 people, after the diet, we've measured their weight again. So weight after diet. And we want to test if the diet has actually impacted the weight or not. Has the weight of these 10 people changed due to this diet? So now we are assuming that the weight before diet is sample A, weight after diet is sample B, and we do a two sample t-test over here. So this is an example of a paired sample because the same observations are in sample A as well as in sample B. They are not independent of each other. So this is an example of a paired sample t-test. Whereas when we are testing the impact of gender on maths, that's an example of independent samples t-test. For example, let's say students want to prepare for GMAT, right? And some students they give the GMAT on, let's say, 10th of April, and then after that they study basis, let's say, the Manhattan preparation technique, and then they give the GMAT again, right? Did the GMAT score change because of Manhattan preparation? So that's an example of a paid sample t-test. On the other hand, I divide the students into two groups. One of the groups does not study Manhattan, the other group studies Manhattan. Both of these two groups then go and give the exam, right? Did the exam performance change, or did one group score more than the other? Did Manhattan impact the performance? So that's an example of independent samples. So typically things like before and after effects are paid sample tests, and two different samples are independent samples test. So does medicine or let's say just does eating or does a certain particular diet impact the weight go down or not, right? When we measure the same set of people before and after, that becomes a paid sample. If we take a certain set of people, divide them into two groups, one gets a diet, the other doesn't get a diet, something like a test and control, so that becomes an independent samples t-test over here. So obviously in independent samples we have already covered that the both samples may or may not have the same size. In paired samples they have to have the same size, so both samples have to be of the same size. So this was a basic example or basic differentiation between independent and paired samples, and I will cover paired samples example more in later. So this was how we did the independent samples t-test on SAS. If I want to test the impact of let's say gender on another subject, let's say in this case I want to test it on, let's pick up another subject. I want to test it on reading ability. So I can just change over here, copy read, go over here, PROC TTEST data equal to dataset name, class remains the same. I simply have to change the var name away from math to read, and I run this test again. I need to look at the unequal variances p-value. The unequal variances p-value is coming out to be about 0.45. This value is greater than alpha, and alpha we've set it as 0.05 or 5%. Therefore, the null hypothesis stays. The null hypothesis was that gender does not impact the science, the read score over here. So this is how we're going to do a two sample t-test on SAS. Let's move on to other tools now. Same data set. I want to test the impact of gender on the math score, and we're going to do it on SPSS now. So I've got the SPSS window open now. To do a two sample t-test, I need to go to analyze, and let's assume, and let's go to the compare means option over here. After compare means, we've already done one sample t-test, and I'm going to do an independent samples t-test over here. Select independent samples. So over here it asks which variable you want to test. So I want to test math, and then it asks the grouping variable, or which variable is creating the samples. So in this case it's the female variable which is creating samples. Define groups. Here you can actually specify if female has got actually more than two samples created, let's say 0, 1 and 2, or A, B and C. In that case, since independent samples can only take two at a time, we have to specify over here. But in this case, since there are only two possible values for female, we don't need to specify anything. Let's check in the options, confidence interval 95%. We don't want to do any missing value analysis, and that's it. So it doesn't allow me to actually press OK. So let's define the groups as 0 and 1 over here, and that's it. So I press continue, I press OK, and we get the results for the t-test. And here we get the t-test and the significance value. So in SPSS, the p-value is defined as SIG, or the significance value. It's coming out as 0.432 over here. And if we compare it with the SAS value, SAS go, yeah. So in fact for SAS we've lost this. Let me run this again. So the significance value, or the t value, was 0.41. The p value is 0.6816. So if I look at the SPSS result, it should come exactly the same. I look at the SPSS result, and there we get the significance two-tailed 0.682 and 0.680. So equal variance is not assumed as 0.682. If I compare it with SAS, we actually get 0.6816, which if rounded down to 3 digits becomes 682. If the equal variance is assumed is rounded down, it becomes only 6.680. So we actually get the exact same result in SPSS as well. So we have to look at the significance column in SPSS. All the other values remain the same. Everything remains the same. Again, we have just done a two sample t-test on SPSS. If I want to do or change the impact from change the impact of gender from maths to, let's say, next was in read, so I can go over here and I click on analyze, compare means, independent samples, remove math, bring in read, press OK, and we get the p-value is 0.457, which is again higher than the value of alpha. Therefore I'm going to accept the null hypothesis, which says that the two samples are the same. Female does not impact the read score. And this is how we do a two sample t-test in SPSS. I'm going to move on to Statistica now. And how do we do a two sample t-test on Statistica? So let's explore the options over here. So we've got statistics options, and let's assume So let me just check which option do we select over here. Let's look at basic statistics. Over here we get the options t-test independent by groups, by variables. So let's look up at t-test by groups independent. Press OK. Select the variable. So the dependent variable, the variable that we are testing. So we want to test math. The grouping variable is going to be female. Press OK and just press summary t-tests. And there we get it. So we get the mean of sample 1, we get the mean of sample 2, we get the t-value, the degrees of freedom, and we get the p-values as well. Right? So please remember that this p-value, which is the p-value of test of variance, is not the same as the p-value of the t-test. So this is the equality of variances test which is conducted in SAS in the end over here. We don't need to look at this value. We can simply look at this p-value which gives us the p-value for the test, which is 0.680, which assumes that the two samples are again not different to each other at all. Right, so this was how we do it in Statistica. I'm going to try and do it on R as well. So pay attention, I'm going to use Rattle over here. So let me open Rattle, library, Rattle, and let's open Rattle. It's taking a little while to open up. So there we've got Rattle now. I'm going to open the same data set, import it. So we've got the HSB2 data set. I've imported. I don't need to partition it for now. And I want to test the impact of read. So I'm going to ignore everything over here. Right, I'm going to test the impact of math. So I press math as the input. I press female as the target. I press execute. Then I go to explore or the test option. I look at t-tests, group by target, which is female. I press execute. Okay, first choose the sample. So I'm going to test math. And there we have it. So the R output is not as clean as the others, but it will give us the same result. So here we get. So we get the two samples, it's called X and Y, observations 91 in one, 109 in the other, mean of X, mean of Y, variance of X, variance of Y. We get the t-value assuming equal variances, and we get the t-value for that t-value we get the p-value as well. So we've got the equal variance assumption and we get a p-value of 0.68 over here. And this is how it's done in Rattle. Now, even though Rattle's output does not look as nice as on the other tools, the great part is this tool is free of cost. You don't need to pay anything. You can download it and run it free of cost. Downside being it takes a little while to get used to it. It's not as user friendly as the others. So this was using all the four tools and doing a independent samples t-test. One more thing where I wanted to quickly cover before we end this lecture. If you want to cover test the impact of the variable on more than one variable at a time, instead of running separately, I can simply still choose and write it over here. So if I want to test the impact of gender on all the scores in one shot, so I don't want to run 5 or 6 different t-tests and compare the results. I want to look at it in one go. So what I can actually do is I can simply type out the variable names in the var section one after the other, var, v1, v2, v3 and v4 and so on. So I'm going to do that over here. So I select read, write, math, science, social studies. So I've got read, math, write, social studies and science. Just checking the spelling. Spelling seems fine. We've got all of this. Close the data. Select the code and I run it. And let's look at the end result. So we get the test for read, which says it's not significant, p-value is higher than alpha. I get the test for write, so one after the other. I look at the unequal variances and I see that in fact the p-value is low. So in fact the right has an impact. So for right, gender is actually impacting the score. So these two genders have got significantly different scores. So I see for one gender the mean score, right score is 50. For the other gender it's 54. And this difference is coming out to be highly significant as the p-value is greater, as p-value is lower than alpha. And as we know, if p-value is low, null has to go, i.e. gender does impact performance on the right scores. So gender did not impact math because p-value is high. But when I look at the right result for right scores, gender has an impact. And that's very, very interesting. Let's move on to social studies. Gender does not impact, p-value is higher than alpha. So you can see p-value for the t-test is coming out to be 0.4446, much higher than the alpha 0.05, i.e. the differences between these two means. So I've got one mean at 52.9, the other at 51.79. This difference between the means is not significant. Whereas in right, and I keep coming back to it, this difference between the two mean is actually very significant. But here, this difference is coming out to be insignificant. Let's look at science. We've got a difference, and this difference is again very large. It's 53 and 50.6. But when I look at the p-value, the p-value is 0.07. It's higher than alpha, so this difference is actually insignificant. And it's higher than alpha when alpha is 5%. But if I change the alpha to 10%, this might actually become insignificant. Uh, uh, sorry, the other way around. So if right now at alpha 5%, this difference is insignificant. But if I change the alpha to 10%, then this difference becomes significant. However, we can't change the value of alpha after getting the result. We have to decide the value of alpha before we do the test. So at 5%, science, the difference in science scores is insignificant based on gender. Let's move on to the other. So that's it. So we've tested the impact of gender on all the scores. Only one score is coming up significant as of now, which is the right score. So we can say that gender impacts the writing performance of the students, but not other subjects at 5% level. If I want to do the same on SPSS, I go to Analyze, Compare Means, Independent Samples T-Test, and Write. I'll select all of these variables in one go. So you can in fact click on the shift button and then click on any button below, and it will select all the variables in one shot. Drag them into the column the area over here. Press OK. And there we get read, write, math, science, social studies all in one shot, and I get the significance over here. So here we see for read scores, the p-value is 0.45, i.e. gender does not impact read. For write, p-value is 0.000. It's lower than alpha. The probability that the two samples are coming from the same population is effectively zero, i.e. these are two different samples, i.e. right scores for boys is very different from right scores for girls. Gender does impact right scores. I look at math. The p-value is again much higher than alpha. It's 0.68. Gender does not impact math. I look at the impact of gender on science, 0.07. It's on the borderline, but it's higher than alpha, i.e. we're going to go with the statement that gender does not impact science scores. And look at social studies. Again, gender does not impact social studies scores as well. And this is how we do independent samples t-test at one shot. Same with the Statistica. If I want to look at Statistica, I can actually go and select more than one variable at one time. So I select read, write, math, science, social studies, and the grouping variable remains female. Press the summary and we get it. So what Statistica does very intuitively is actually figures out which variable is getting impacted and it highlights it in red. So as you can see for right, it's highlighted it in red because the p-value is low. It's lower than 5%, i.e. only right is coming significant. No other variable is coming up as significantly impacted by the gender variable. Right? So this was the independent samples t-test tutorial. And in the next class, what we will do is I'll give you an example of paired samples t-test. And Any other questions, etc., please you feel free to mail them to me or discuss this in the discussion forum.